Hello friends, a warm welcome to this session on the flyback converter. Our aim is to teach you the practical design of a flyback converter. However, before we jump into the practical design, it is essential that your theoretical concepts are absolutely clear, and therefore we are conducting this session which covers the basic concepts of the flyback converter. So let's jump right into it. The first question one would obviously ask is, what is a flyback converter? Most standard textbooks of power electronics give the definition as a DC to DC converter that provides isolation between input and output. There are some important terms in this definition that we need to understand. The first is the DC to DC converter. So what is a DC to DC converter? It is basically a circuit which converts input DC voltage to an output DC voltage of an other level. If the level of output DC voltage is higher than the input DC voltage, it is referred to as a step-up DC to DC converter. On the other hand, if the output DC voltage is less than the input DC voltage, it is referred to as a step down DC to DC converter. Another term which we need to understand in this definition is isolation. Isolation here actually means electrical isolation. Isolation tells us that there is no electrical connection between the input and the output of the converter. As we study the circuit of the flyback converter, you will observe a very important component which is used in it, mainly the flyback transformer, which is nothing but mutually coupled inductors. In fact, this circuit gets the name flyback converter mainly on account of the use of flyback transformer, which actually, as I've already mentioned earlier, is mutually coupled inductors. I would like to dwell a little more on the isolation topic. In this circuit, energy from the supply is stored in one interval. Maybe we can call it as T on. At that time, source is connected and load is disconnected. And in the subsequent interval, energy stored is delivered to the load. At this time, the source is disconnected and the load is connected. This interval may be designated as T off. So you can see there is a clear demarcation, a time demarcation between taking energy from the source and delivering this energy to the load. This characteristic is responsible for excellent isolation provided by the circuit. Now coming to the applications of the flyback converter. Typically, the flyback converter handles power ratings up to 100 watts and is very suitable for design of most cell phone, tablet and laptop chargers. Now let's get into the circuit of the flyback converter. As you can observe on your screen, this particular circuit has surprisingly got a very low component count. In fact, it has only 4 components. You require only 4 components to construct this circuit. Let's have a closer look at it. The first component is the flyback transformer, which is responsible for providing the isolation function and of course is very important to the operation of the converter. Then we have the switch. The switch used in this circuit is the MOSFET. At the gate of the MOSFET, we apply the gating signal. This is the primary side of the flyback transformer. Similarly, when we go to the secondary side of the flyback transformer, you will find there is a rectifier diode and a capacitor C. Now all the components which are used for the construction of this circuit are assumed to be ideal in our analysis. Also, another important point to be noted is regarding the capacitor C. It is assumed to have a high value of capacitance. Due to this, the voltage across the capacitance can be assumed to be constant, which we take as a value V0 in spite of load variations. Now let's see a little more about the signal applied to the gate of the MOSFET. The gating signal is basically responsible for turning on and turning off the MOSFET. When the gating signal is high, the MOSFET turns on. When the gating signal is low, the MOSFET turns off. As you can see in the circuit itself, when the MOSFET is on, the supply delivers power to the primary of the transformer. And when the MOSFET is off, it will act like an open circuit, so no current and hence no power will be drawn from the supply. Let's have a closer look at the gating signal. Now if you look at the gating signal, it is a series of rectangular pulses. The pulse has an amplitude Vg. The period of the gating signal is T. The gating signal is high for an interval T on, referred to as the on time, and the gating signal is low for an interval T off, referred to as the off time. T on mainly to signify the duration for which the MOSFET is on, and T off mainly to signify the duration for which the MOSFET is off. Just to so that you can recollect better, this is the MOSFET. If we give a high gating signal here, the MOSFET will turn on, and if we give a low signal here, the MOSFET will turn off. We will be studying details of this when we actually go into the operation of the flyback converter. So let's take one more look at the gating signal. Get this picture very clear in your mind because you will require this in every step of the operation. You'll have to visualize what kind of signal is given to the gate, which will result in the MOSFET turning on or off. Now let's go into the operation of the flyback converter. The operation of the flyback converter can be analyzed in two intervals. The first interval, as you can see on your screens right now, is the T-on interval, where we consider operation during the interval from 0 to T-on, T-on not included. The second interval is in the duration T-off. This includes the time from T-on to T. As you can see on your screen, this interval is clearly indicated. Now we will discuss the operation in each of these intervals one after another. So let's get into it. The first case of operation is the Teon interval. So let's get into it. Observe the circuit on your screen very carefully. When a high voltage is given to the gate at t equal to 0, the MOSFET turns on. That is, it acts like a short circuit or a closed switch. Hence, the supply voltage Vs now appears across the primary winding. That is V1 equal to plus Vs. Also, there will be current flow in the primary winding. This current is increasing from 0 onwards. Due to this increasing current, the flux phi in the core also starts increasing from 0. This increasing flux is linked to the secondary winding Ns, and hence it induces a voltage V2 in the secondary winding. The polarity of the voltage is as per the dot convention. Voltage across the secondary winding can be obtained as per the standard transformer equations. As you can see on the screen, the voltage is calculated to be Ns upon Np into input supply voltage Vs. Now let's study the status of the diode D. If we apply KVL to the secondary loop, we find that the anode to cathode voltage of the diode is negative, and hence the diode is in the off state, and therefore it acts like an open circuit. This is as shown in your screen right now. Because the diode acts like an open circuit, the secondary is effectively open circuited, and hence the diode current is zero. Now if we look at the status of the load and the capacitor, the load is disconnected from the circuit effectively, electrically disconnected from the circuit. Then from where is the load getting its power? As you can see, the capacitor voltage, the capacitor is supplying the energy to the load. Capacitor has a large value of capacitance. We had earlier mentioned it. Hence, the voltage across the capacitor can be considered to be constant. This voltage appears across the load, and the capacitor can be considered to be driving the load. Hence, the load current, as you can see on your screen again, is IR is equal to VO upon R. VO is a constant voltage, R also is a constant, hence the current through the resistance is also constant. However, note that it's very important to note that the power drawn by the load here is from the capacitor and not from the source. Now, let's analyze the circuit a little more further. The winding Ns, which is the secondary winding, as we have mentioned earlier, will be effectively open because the diode is open circuited. On account of this, we can actually do away with the secondary circuit. This will cause us to consider the primary winding Np with its magnetic field around it as a simple inductor with a voltage Vs across it. So the basic inductor equation can be applied to this circuit, and after doing the basic analytics, we will find that the primary current is directly proportional to time. That is, the primary current increases linearly with time. We knew earlier that the primary current is increasing. We knew that this primary current is flowing through the inductor. We knew that current flowing through the inductor causes a flux to be produced in the core. We knew that the flux through the core is also increasing. But now what we are seeing is the increase is linear. The current and hence the flux increases linearly with time, because flux is directly proportional to the primary current. Now this is the basic operation which happens during the interval T on. We will find that the primary current is increasing linearly, hence the flux is also increasing linearly. The secondary has no effect as such on the primary. The secondary circuits, that is the capacitor and the load, are effectively out of the circuit. Let us now look into the waveforms for the duration T on. You may pause your video for a moment to study the waveforms. Right. Now let's have a look at these waveforms. During the interval T on, as you can see, the gating signal is at a level Vg. Hence, the MOSFET is on. Now, because the MOSFET is on, the voltage across the MOSFET switch is 0. The primary current, as we know, is increasing linearly with time. And this current will continue increasing till it reaches a value IP max at T on. Similarly, the core flux, which is directly proportional to the primary current, will also increase linearly till it reaches the value phi max or phi m as it is shown there at the instant T on. If you look at the diode current, since the diode is in the off state, the diode current during the Teon interval is 0. The primary voltage has a value Vs, the supply voltage. We have already said because the MOSFET switch is closed, the supply voltage Vs appears across the primary winding. The secondary voltage is Ns upon Np into Vs, as has already been discussed earlier by the simple transformer equation. So these are the waveforms which you need to understand for the interval T on. What we are discussing here is the interval from 0 right up to T on, but not including the instant T on. From T on to the time period T, we will be discussing in the next section. We shall now discuss the operation of the converter for the interval T off. This is the duration beginning from T equal to T on right up to the end of the time period T. So let's get into this discussion. First, we need to understand the status of the gating waveform at T equal to T on. As you will observe, at the instant T equal to T on, the gating waveform has two values. As you can see on your screen, the gating waveform has a value Vg and a value 0 at the same instant T on. This is because we are considering an ideal situation. In practice, it is not possible to have two values at the same instant. When the gating signal has value Vg at T equal to T on, for our reference, we will refer to it as T equal to T on gate high. Similarly, when the gating signal has a value 0 at T equal to T on, we will refer to it as T equal to T on gate low. Now, let's go into the operation of the circuit for this duration. At T equal to T on gate high, the current IP has reached maximum value IP max, and hence flux reaches maximum value phi m. You can see here on the screen we have labeled IP equal to IP max, and your flux value is labeled as phi m, which denotes the maximum flux. Now at this instant, the MOSFET gate voltage transitions from high to low. This will cause the MOSFET to turn off at the instant T equal to T on gate low. Hence the MOSFET will act as open circuit. Note here, at T equal to T on high, your current IP has got a maximum value, flux has got a maximum value. Now your gate signal transitions from high to low. So at the instant T on gate low, your MOSFET turns off, acts as an open circuit. Due to this, the primary current in the circuit will rapidly drop to 0. On account of this, the flux, that is the magnetic flux, will also tend to reduce. This will cause a voltage of reverse polarity to be induced in both the windings. Now you need to note that during the duration T on, the primary current was increasing, hence the flux was also increasing. Therefore, we considered the induced voltage in both the windings to be of one particular polarity. Now, the flux is tending to decrease, and that is the reason why the voltage induced in both the windings will be of opposite polarity. This is as shown in your screens right now. You can see how the reverse polarity in both the windings look like. The voltage induced in the secondary winding Ns will be of such a magnitude and polarity that it will effectively forward bias the diode D. Hence, the diode D will act like a closed switch. This will cause a current Imax to flow into the secondary at the instant t equal to T on gate low. Note the instant. The current Imax is flowing in the secondary circuit at t equal to T on gate low. The value of Imax equal to Np by Ns into Ip max. The direction of diode current flow in the secondary winding is as shown. The value of Imax is such that the magnetomotive force Ns into Imax generated in the secondary winding at T equal to T on gate low will be equal to the magnetomotive force Np into Ip max generated in the primary winding at T equal to T on gate high. This ensures that maximum flux phi m is maintained in the core at T equal to T on gate low even after transition of the gate signal from Vg to 0. A very important point to note is that at T on gate high, primary current is maximum at Ip equal to Ip max and diode current ID flowing in the secondary equal to 0. Hence, at this instant, maximum flux phi m in the core is driven only by the primary winding magnetomotive force. However, at T on gate low, the primary current Ip equal to 0 and the diode current flowing in the secondary is maximum at Id equal to Imax, which maintains the flux phi m. Thus, at this instant, maximum flux phi m in the core is driven by the secondary winding magnetomotive force only. Note that the magnetomotive force created by the secondary winding at T equal to T on gate low is equal to the magnetomotive force created by the primary winding at T equal to T on gate high. So let's have a look at the waveforms to complement our discussions. Remember, we are at the instant T on right now. The gating signal is falling from the level Vg down to 0. At this instant T on, you will find that the primary current has a value Ip max and the current drops down abruptly to 0. If you look at the core flux has a value phi m or phi max, and this core flux is tending to decrease. It is tending to decrease. Although it is phi max at the instant t on, it is tending to decrease subsequently in the cycle. And therefore, you will find that the polarity of voltages induced in the two windings have reversed. If you look at the diode current, the diode has turned on because of effective forward bias on account of voltage of proper polarity being induced in the secondary. Now this diode current you will see is I max at the instant t equal to t on. Look at the relationship here. The primary current has gone from the maximum value down to 0 abruptly, and at the same instant the secondary current has risen from 0 to a value I max. There is of course a distinct relationship between the two currents as per the transformer equation. Then you will look at the secondary voltage. Because the diode is on, the output voltage will appear across the secondary. We shall see this in the subsequent discussion. And this voltage will appear across the primary after multiplication by the term Np by Ns. If you look at the voltage across the MOSFET switch at the instant t equal to T on, you will observe that the voltage has jumped from 0 to a high value. This high value is, as you can see, Vs plus Np by Ns into Vo. We calculate this voltage by applying KVL in the circuit, which we shall discuss in a short while. So this is about the waveforms for the different points in the circuit. Since the MOSFET switch acts as an open circuit, hence the primary winding is effectively open circuited. Therefore, it will have no effect on the secondary winding. Now, the secondary winding with the magnetic field around it will act as a simple inductor. Hence, the basic inductor equation can be applied to the secondary winding. That is V2 equal to Ls into dId by dt. Also, the current Imax can be considered as the initial current flowing through this inductor. Note that Imax is the secondary current at T equal to T on gate low. You will recollect this from our previous discussion. Now we apply KVL to the secondary circuit. After performing some basic mathematical analysis, we arrive at the equation Id of t equal to Imax minus V0 by Ls into t. This equation is highlighted on your screen. If we look at this equation, you will observe that V0 and Ls are constants. Hence, we can conclude that the diode current will decrease linearly with time from the maximum value Imax towards 0, and all this happens during the T off interval. Hence, the core flux phi also reduces linearly towards 0 during this T off interval. As the diode current decreases linearly towards 0, a stage is reached when the diode current will touch 0. At this instant, the diode turns off and the core flux reduces to 0. Since the diode is off now, the load capacitor circuit is electrically disconnected from the secondary winding. Hence, the voltage across the secondary will be 0. On this account, the voltage across the primary will also become 0. Also, if you observe the circuit, you will find that the capacitor is now the source for the load. The capacitor supplies a constant voltage to the load. The capacitor also drives current through the load. This is the status quo which is maintained till the end of the cycle. Let's now look into the waveforms for the duration T off. Let's look at the gating signal first. During the interval T off, the gating signal is at a low level. Next, let's look at the primary current. At the instant T equal to T on gate low, the primary current is 0 and it continues to be 0 till the end of the cycle at T. The diode current at T equal to T on gate low is at the level I max. This current, which is also the current flowing in the secondary winding, decreases linearly with time until a stage is reached when this current becomes zero, at which point the diode turns off. Further, the current remains at zero level till the end of the cycle. At T equal to T on gate low, the secondary voltage is at a level VO, and this level is maintained for the duration the diode is in the on state. The primary voltage as a consequence will also be maintained at a constant level for the duration the diode is on. If you look at these three waveforms, you will see that for the duration the diode is conducting, that is current flowing in the secondary, the primary and secondary voltages are constant. Note that the voltage V0 appearing across the transformer secondary is due to the fact that the capacitor appears across the secondary, and this capacitor has a fixed voltage V0. Why the capacitor appears across the secondary? The reason is the diode is on. Now, when the diode current becomes zero, at that instant the diode turns off. Hence, the capacitor is no longer connected across the secondary. So the capacitor voltage V0 no longer appears across the secondary, and hence the secondary voltage drops to zero. The same will therefore happen to the primary voltage, and this status of zero voltage level across the primary and the secondary windings is maintained till the end of the cycle. Now let's discuss the voltage across the switch, the MOSFET switch. At the instant T equal to T on, gate low, the MOSFET switch is at a level, as you can see, Vs plus Np upon Ns into Vo. Effectively, the voltage across the MOSFET switch is the summation of supply voltage and the voltage across the primary. During the interval Td, which is the time the diode is on, primary voltage is present. Hence, you are going to get the total voltage across the MOSFET switch as what is shown there, Vs plus Np upon Ns into Vo. However, at the instant the diode current becomes zero, the voltage across the primary also becomes zero. Hence, you will find that now the voltage across the MOSFET switch, which is effectively a summation of the supply voltage and the primary voltage, Vs plus Vp, but now Vp is zero. So the voltage across the MOSFET switch reduces from its high level to the level Vs, and this status is maintained till the end of the cycle. This section gives the derivation for the output voltage of the flyback converter. You may pause the video and go through each step of the derivation. It is very important to keep in mind the principle on which the derivation is based, which is power supplied by DC source is same as power absorbed by the load resistor. Once you understand this basic principle, looking at the circuit alongside and the theory which you have studied so far, you will be able to understand this derivation. Let us take a look at the expression for the flyback converter output voltage, which is highlighted on your screen right now. It will be observed that for a given switching frequency and constant load, constant primary inductance, and constant input voltage Vs, the output voltage is directly proportional to the duty cycle D. This dependency of the output voltage on the duty cycle is an important characteristic for implementing output voltage regulation. Regulation action is incorporated in the converter by including a feedback network which adjusts the duty cycle appropriately when the output voltage changes from its set value. This action of appropriate duty cycle adjustment pulls the output voltage back to its set value. Details of feedback circuit and its working will be covered in a later module. Thank you.